This lecture video will cover differential rate laws. Please read the OER textbook chapter section 12.4 for more details. The differential rate laws provide a mathematical expression of how changes in the concentration of a reactant affect the rate of chemical reaction. Please note that the differential rate law can only be determined from the experimental data. Okay, so this is come only from the experimental data. So let's take a look at this. Okay, so this reaction is what we see in the lecture demo in the previous video. Okay, so this reaction is between sodium thiosulfate and hydrochloric acid that forms solid sulfur. So this is yellow color. So if you remember one of the lecture video that we looking at the factor that affect the rate of reaction, right? You see that once these two react, it's going to produce like the yellow solid in a test tube, right? So we're looking at that before. So what we are going to take a look at is we are going to take a look at the experimental data to help us determine the differential rate law. Okay, so in this case, what you are going to be given is you are going to be given several series of the experiment, and you are going to be given the different concentration of the reactant, and it's going to give you the initial rate. Okay, so as we know, right, the initial rate is the rate at time equal to 0. So it's going to be the maximum rate, right? So go back into, refer that to the previous lecture video. The differential rate law will tell us about the relationship between the concentration of the reactant and the rate, right? So for example, what happened if you change this concentration, how would that change the rate, right? Same thing for this one as well. Like if you change the concentration of hydrochloric acid, how would that affect the rate, right? So that means we will need to be able to write out the mathematical expression for this, which is what we call rate law expression. Okay, so rate law expression is going to always start with the relationship between rate, okay, equal to the concentration, but it's going to multiply by a certain constant, case K. So this constant right here is going to be the rate constant that I mentioned earlier in the previous lecture video. Okay, rate. We already see this before, right? In terms of average rate or instantaneous rate from the first lecture video for this chapter. Okay, so this is the reaction rate. Okay, it's going to be in the unit of molar per second. Okay. Then we are going to relate between rate and the concentration, right? So that means in this case, the concentration would be the concentration of the reactant. Okay, so it's going to be sodium thiosulfate. Okay, we are going to raise this to a certain power. So I'm going to use that as X. Okay, so this X right here is what we refer as reaction order. Okay, it's going to tell us how changing the concentration affect the rate. Okay, so, and then we need to include all of the reactant, right? So in this case, we need to include hydrochloric acid as well. And I'm going to raise this to the power of Y. I don't know what is X and Y yet. Okay, so again, both X and Y are what we refer as reaction order. Okay, so it's going to tell us how changing the concentration affect the rate. These X and Y can only be determined from the experimental data. So for example, in this case, I'm going to find out X and find out Y from using this given data. So how can we do that? Okay, so we are going to use this rate expression here to help us to determine X and Y. Okay, so remember the rate constant is a constant value, so that means it will never change. Okay, so this is always stay the same. Okay, regardless of you are changing the concentration or not, this rate constant is always going to stay the same. Okay, so the only time that the rate constant is going to change would be when you change the temperature, as we see in the Arrhenius equation, right? So as temperature increase, right, the K value increase from the previous video. So in this case, we are not changing the temperature, so we are going to keep the temperature constant. So therefore, the K value is going to constant throughout the experiment. So that means experiment 1, 2, and 3, they all are going to have the same value of K. Now, the next thing is, how do we calculate for X and Y? Okay, so when you are calculating for X and Y, you will need to use two experimental data to compare, right? Because you are looking at the change, right? How changing sodium thiosulfate will affect the rate, right? So in this case, you are going to take a look at the change in concentration of the reactant. Remember, if you are going to find out the unknown variable, you have to keep the other one constant, right? So if you change both of them, you are not going to be able to find out the unknown variable because changing both you are going to, it's going to affect everything, and it's going to make everything too complicated. So in this case, when we are looking at the differential rate law, we're looking at the relationship between rate and the concentration of the reactant, right? So in this case, if you want to know how the change of concentration of sodium thiosulfate affect the rate, then you need to keep the concentration of hydrochloric acid constant, right, in order to see the true effect of sodium thiosulfate. Vice versa, if you want to know how the concentration of hydrochloric acid is actually affect the rate, then you will need to keep the concentration of sodium thiosulfate constant, so that way you see only one effect at a time. Okay, so that's what we are going to do now. Okay, so in order to find out X and Y, you will need to choose the correct or the proper experiment value. Okay, so in this case, I'm going to need a little bit more space here. So I'm going to use this small table instead. It's still, everything's still the same. Okay, so I just decreased the size of the table. Now let's find X. Okay, so as I mentioned earlier, in order to find X, which is going to be how the change of sodium thiosulfate affect the rate, you will need to keep the concentration of hydrochloric acid constant. Okay, so that way we eliminate the effect of hydrochloric acid. Okay, so in this case, what you are going to do is that you are going to choose the experiment that have the same value of the concentration of hydrochloric acid. So in this case, you can see that the experimental 1 and 2 have the same value of the hydrochloric acid. So that means in this case, concentration of hydrochloric acid be kept constant. So that means you are going to see that how changing concentration of sodium thiosulfate would affect the changing of rate. What you are going to do next is you are going to have to set up the rate expression again. Okay, so in this case, I'm going to use the rate that have higher value. So in this case, it's going to be experimental 2. Okay, so experimental 2 has higher rate than experimental 1. So I'm going to set up rate of the experiment 2, okay, equal to the K constant, right, which is, this is going to be the rate law expression that we wrote out earlier, times sodium thiosulfate from the experimental 2, right, raised to X, right, multiplied by concentration of hydrochloric acid, okay, from the experimental 2 raised to Y. And you are going to divide this by the rate from the experimental 1. Okay, so K1 times sodium thiosulfate from experimental 1 raised to X, hydrochloric acid, right, from experimental 1 raised to Y. You will see that in this case, K is the constant. So therefore, you can actually cancel that out, right, because they are the same. They're going to be the same anyways. You can see as well, hydrochloric acid is going to be constant as well, right, because 0.2 and 0.2, if you replace those, you are going to see that they are going to be able to cancel out from each other as well. So the next thing is I'm actually going to replace all this rate and the concentration by the actual value that we have. Okay, so let me do that. So I'm going to erase this with the actual value. So the actual value from the experimental to the rate is going to be 0.22, right? So this is one right here, 0.22 molar per second. And the concentration of sodium thiosulfate is 2.0 molar. And Y is 0.2 molar. Okay, so now let's take a look at rate 1. Okay, so from the experimental 1. And replace all of this from the experimental 1 as well. Okay, so now if you're looking at experimental 1, you will see that the rate is 0.11. Okay, sodium thiosulfate is 1.0 molar and hydrochloric acid is 0.2 molar. Okay, so as you see, right, the concentration of hydrochloric are the same. So these two values are going to be able to cancel each other out. So what you're going to have is that you are going to have, so that is going to come out equal to 2, right? It's going to equal to, so this one right here, right? So pretty much you are going to see that is 2 over 1, right? Everything to the X, right? So in this case, the same as 2 to the X. Okay, so what should be the exponent of X then? Okay, so we know that when X equal to 1 or 2 raised to 1 is equal to itself. So in this case, therefore, we know that X is equal to 1. Okay, so now we got the reaction order of X equal to 1. So what happened if you don't know what is the exponent, right? So what you are going to do is that you can use the log as well to help you with this, right? So if you use log of 2 and log of this, if you put log on both sides, you are going to be able to bring the x down. Okay, so in this case, you are going to be able to bring x log of 2, okay, so equal to log 2. And then you are going to divide both sides by log 2. Right, so therefore, your x is going to come out equal to 1. Okay, so you can do either way. All right, so now we know x. The next thing we're going to do is we are going to find out y. Okay, so to find out y, you will need to keep the concentration of sodium thiosulfate constant. And if you're looking at the experiment, experimental 2 and 3 are going to be the one that we will need to choose, because in this case, concentration of sodium thiosulfate is kept constant. Okay, so, and I'm going to set up in such a way that the higher rate would be on top, so that way you don't get the fraction. So in this case, I'm going to use rate 3 over rate 2. Okay, so I'm going to set up the same thing. Okay, so if you do rate 3 over rate 2, you're going to get 0.23, right, from rate 3 molar per second equal to rate constant times concentration of sodium thiosulfate, which is 2.0 molar. You can plug in the x as well. In this case would be 1, right, because we already know x, and then multiply by concentration of hydrochloric acid, which is 0.1 molar to y. You're gonna divide this whole thing by rate of experimental 2, which is 0.22 molar per second, K is constant, divide by concentration of sodium thiosulfate from experimental 2, right, divide by concentration of hydrochloric acid from experimental 2. So you can see that the rate constant will cancel out, right? Its concentration of sodium thiosulfate will cancel out. And if you find out the value of this, okay, so it's going to come out to be about 1, right? Which is equal to, in this case, it's going to be 1 over 2 raised to y. Okay, so what is the order? What is the exponent that when you raise something is equal? So if you raise anything with 0, so 1 over 2 raised by 0 is going to equal to 1. So in this case, you will know that y would equal to 0. Okay, so if I don't know, what do I do? So again, you need to take log again. Okay, so if you do log of 1, log of this, you are going to get you are going to end up getting log of 1 equal to y log of 1 over 2 is 0.5, right? Log of 0.5. And then you are going to divide both sides by log of 0.5. You are going to solve for y. Okay, so in this case, you are going to get y equal to 0. Okay, so you can do either way. You can take log on both sides, or you can just know that anything raised to 0 is equal to 1. Anything raised to 1 is equal to itself. So on the exam, I expect you to actually show me work like this. Okay, so in order to determine the reaction order. All right, so now we know the x and y. So then all we need to do is put them all together as the rate law expression. So that means in this case, the rate law expression for this reaction would be rate, okay, equal to the rate constant times concentration of sodium thiosulfate, okay, times concentration of hydrochloric acid raised to 0, this one raised to 1. Okay, so remember, anything raised to 0 is equal to 1. So that means another way to write this rate law would equal to rate equal K times just the concentration of sodium thiosulfate. Okay, so that. The reason for that is because anything, again, raised by 0, right, is equal to 1, right? So in this case, imply this is equal to 1. Okay, so you can write either way. Okay, so you can include all of those x and y, or you can omit the one that have 0 order. What does this rate law tell us then? Okay, so this rate law tell us how the change of the concentration affect the rate, right? So that means in this case, if you change the concentration of sodium thiosulfate, okay, so it's going to directly change the rate. For example, if you double this, the rate is also going to double. If you triple this, the rate also going to triple. That's what it tells us. Okay. when you are looking at the effect of the concentration of hydrochloric acid, however, it's going to be not the same effect as sodium thiosulfate. Okay, so now if you're looking at concentration of hydrochloric acid, you can see that the change of the concentration of hydrochloric acid doesn't affect the rate at all. Right, so that's why when you change this concentration, that's why the rate is still the same. Okay, so that means zero reaction order tell us that the concentration of that reactant doesn't affect the rate. That's what it means. According to this rate law, we can say that this reaction is first order with respect to the concentration of sodium thiosulfate, and it is zero order with respect to the concentration of hydrochloric acid. The next thing we're going to take a look at is the overall order of reaction. Okay, so the overall means you're going to add all of the order together, right? So you're going to add X and Y order together. So in this case, it's going to equal to 1, or what we call first order. Okay, so this is first order overall reaction. So the next thing is we are going to determine the rate constant or the value of K now. Okay, so with proper units. Okay, so note that as I mentioned before, the K is the rate constant. It will never change. So therefore, you can choose any trial to calculate for K because it's going to give you the same value. Now let's calculate for K. Okay, so again, you can choose any experiment. So I'm going to choose 1. Okay, so you can do 2 and 3 as well, and you should get the same K value. Okay, so if you choose 1, okay, so all you need to do is that you are going to replace all of this concentration to the rate law expression. Okay, so according to rate law expression, right, we know that the rate, which is 0.11 molar in this case per second, right, according to that, is going to equal to, next is multiply this K with the concentration of sodium thiosulfate. Okay, so it's going to be 1.0 molar raised to 1 is equal to itself. Okay, so I'm just going to leave like that. Okay, so that's come from that. Okay, so the second one is hydrochloric acid. You don't have to include this part because hydrochloric acid is going to be raised to power of 0, which is going to equal to 1. So you can just omit like that. Okay, so in this case, you just solve for K. Okay, so I'm going to divide both sides by 1.0 molar. Okay, so you're gonna see that molar concentration will cancel out. So in this case, your K value would come out equal to 0.11 per second. Okay, so that would be your correct value of K and also proper unit for K as well. Okay. So what does this K tell us? Well, if you put this together, right, so you can actually now replace this K with the value that we just calculated. Okay, so you can replace those K with the value that we just calculated. The rate law with the known value of K is very useful because it can be used to predict the rate of other condition that we have not run as well. What do I mean by that? Okay, so let's take a look at number 4. Okay, so if you're looking at number 4 here, you can see that for number 4, right, is asking you to find out the rate of reaction that involved with the concentration at 4 molar of the sodium thiosulfate. If you're looking at the experiment, right, we don't have 4 molar. It's giving us only up to 2 molar. So that means this is outside the range that we already conduct the experiment. Okay, so that means in this case, instead of run the experiment again, you don't have to. You can use this equation right here to actually calculate for the rate at different condition. Okay, so that's the beauty of this. Okay, so rate law can be used to predict the reaction rate at different concentration of the same reaction at constant temperature. Okay, so how can we do that? Okay, so what I'm going to do is I'm going to use the same rate law equation that we did earlier, which is rate, right, equal to K. But now we know the value of K. K is 0.11 per second, right, multiplied by the concentration of sodium thiosulfate, right, raised to 1 is equal to itself. And then hydrochloric acid is raised to 0. So that's why I'm excluding this case because it's equal to 1. So in this case, I want to know the rate at which concentration of sodium thiosulfate is equal to 4 molar. So that means in this case, you can also write out concentration of hydrochloric acid as well, but just make sure that this is raised to 0, right? So to find out rate is going to equal to 0.111 over S, right, times concentration of sodium thiosulfate. In this case, it want to know at 4 molar. So 4 molar, okay. And then 4 molar for hydrochloric acid, but it's raised to 0. So that means in this case, this part right here is going to equal to 1. So that means you can actually eliminate that, right? So that means in this case, the rate at this condition, okay, the rate would come out to be 0.44 molar per second, right? Because you multiply molar and per second together. Okay, so which makes sense because the rate unit is going to be the amount per time, right? So molar per second. Okay, so in this case, number 4 would be 0.44 molar per second. Okay, so this lecture video so far, you learn how to find out the reaction order. Okay, you learn how to find out the rate constant, and you learn how to use the rate law expression with the proper reaction order and proper rate constant to find out the rate of reaction at different conditions. Okay, so my expectation is for you to be able to do all of this on the exam. All right, so now let's understand the reaction order real quick. So as I mentioned earlier, the reaction order will tell you about the relationship between the concentration, how the concentration change, right? How it affect the rate, right? So in this case, let's take a look at zero order. Okay, so if you're looking at zero order as you see it previously, right, from hydrochloric acid, right, you can see that when you change the concentration, it doesn't affect the rate at all, right? The rate stay the same, right? So that means in this case, the rate law that you will see, you are going to see that the rate would equal to the rate constant. So that means the concentration of the reactant doesn't have any effect on the rate at all. So again, zero order tells us that the reaction rate is independent of the concentration of the reactant. Now let's take a look at first order reaction. Okay, so this is going to be similar to the sodium thiosulfate that you see earlier, right? When you see the first order, you can see that the change of the concentration of the reactant would affect the change of rate, right? So as you change this, the rate will change as well. Okay, so let's take a look at this. Okay, so when you're looking at the concentration of A, right, when you double it, right, so go from 0.1 to 0.2, you also observe that the initial rate also double as well, right? So that means in this case, when you see something double, the rate double, that is going to imply that that is going to be first order. If you quadruple, right, the rate also quadruple as well. So that means this one is going to imply that this is going to be first order. So that means for first order reaction, you are going to observe that the rate is going to be directly proportional to the concentration. So that means the first order tells us that the reaction rate is directly proportional to the concentration of the reactant. Now, second order, you have not seen that yet, but I want to mention this. Okay, so for second order, it's going to be, the rate is going to be directly proportional to the square of the concentration of the reactant. So what do I mean by that, right? So for example, if you double the concentration of the reactant, right, you are going to see that the rate is going to quadruple. That means in this case, the second order tells us that the reaction rate is going to directly proportional to the reactant square. Okay, so all the reaction rate increase exponentially as the concentration of the reactant increases. Okay, so now here is the graphical representation of zero order, first order, and second order. Okay, so if I plot between rate and the concentration, okay, so this is what zero order is going to look like. Okay, so remember, zero order is when you change concentration of the reactant, the rate stay the same, right? So that means in this case, zero order is going to look like that, right? So it's not going to have any change in terms of rate. Okay, for first order, okay, as you see, for first order, rate of reaction is directly proportional to A. Therefore, in this case, if you plot between rate and A, right? So this is Y, this is X, you are going to see a positive slope like that. Okay, so as the concentration increase, the rate increase. For second order, right? So as you see, right, the rate is directly proportional to A squared. So in this case, you are going to get the exponential graph like this. Okay, so here are the three different graphs. If I show you graph like this, you need to tell me which one would that be, right? Whether it's going to be zero order, first order, or second order. Or I might ask you to draw the graph like this, right? By giving you that, what is the graph of first order? You need to be able to draw me that. Okay, so that would be expectation. Okay, so now it's your turn now to actually complete this example one. Okay, so I want you to use the scenario that we learned before in terms of reaction between sodium thiosulfate and hydrochloric acid and apply that to this example. Okay, so I want you to find out the rate law expression, and I want you to find out the overall reaction order and find out the constant K for me, and also giving me the rate at different concentration that is not part of this experiment. Okay, so let's pause the video now and complete this. Okay, and then resume the video again when you're ready. Now let's check your work together. Okay, so in this case, we are going to write out the rate law expression, which is the equation that expresses the relationship between rate and the concentration of the reactant. Okay, so in this case, it's going to be rate equal to K, right, multiplied by concentration of nitrogen monoxide. Okay, so raised to X, and then oxygen gas raised to Y. Okay, so our goal is we need to find out X and Y. On the exam, you cannot leave me just this. Okay, so this is tell me nothing about the relationship between concentration and the rate. Okay, so you need to find out the order of reaction X and Y. Okay, so to find out X and Y, okay, so first thing we are going to find out X. If you find out X, you will need to keep oxygen constant. So we are going to choose 1 and 3. Okay, so in this case, if you choose 1 and 3, you are going to set it up as, okay, so let me do this. Okay, so I'm going to use rate 3 over rate this case. So it's going to be 2.14 times 10 to negative 1 molar per second, okay, equal to concentration of, K times concentration of nitrogen monoxide raised to X, right, and then concentration of oxygen raised to Y. Okay, so in this case, we are going to divide this whole thing again by experimental 1. Okay, so 8.55 multiplied by 10 to negative 3 molar per second. Okay, and then concentration of nitrogen monoxide would be 0.030 and 0.0055 molar for oxygen. Okay, so again, this is belong to experimental 3. Okay, so this is belong to experimental 1. Okay, so now you are going to cancel all those constants. Okay, so K cancel out, unit molar per second will cancel out, concentration of oxygen will cancel out. Okay, so what you are going to get would be this value divided by each other. Okay, so you're gonna divide this value by each other. So you are going to get 25. Okay, so is equal to, now we are going to divide this value by each other. Okay, so if you do that, you are going to get 5x. Okay, so one of the exponent property is that when you raise something by the same power, right, you are going to be able to combine the power. So for example, in this case, right, this is going to equal to 0.150 over 0.03 raised to X. So that's how I get 5 right here. Now the next thing is to find out X. Okay, so we know that 5 squared is equal to 25. Therefore, in this case, we know that X would equal to 2. Okay, so again, if you don't know how to do this, what you need to do is you will just need to use log on both sides. Okay, so, and then if you put log on both sides, the exponent is going to come down. Okay, so you're gonna get log of 25 equal to X log of 5. And then you are going to divide both sides by log 5 to solve for X. Okay, so you are going to see that X will come out equal to 2 in this case. Okay, so now we know one value. So we know that per concentration of nitrogen monoxide, we know that the reaction order would be second order. Okay. All right, so the second one is we are going to find out Y now. Y, when we find out Y, we will need to keep the concentration of nitrogen monoxide constant. So we are going to use 1 and 2. Okay, so I'm going to set up the same thing. Okay, so in this case, I'm going to use experimental 2 divided by experimental 1. Okay, so I'm going to do 1.29 times 10 to negative 2 molar per second equal to K times concentration of nitrogen monoxide. Okay, multiplied by concentration of oxygen divided by experimental 1. So it's going to be 8.55 times 10 to negative 3 molar per second equal to K times concentration of nitrogen monoxide and multiplied by concentration of oxygen. Okay, so now I'm gonna eliminate that unit, right, this unit as well, and this is going to be canceled out. Okay, so now we are going to combine this. Okay, so you are going to calculate for this result. And then remember, we can also, this one can also be right as 0.0083 divided by 0.0055, and then both of them raised to y. Okay, so if you calculate for this, you are going to get 1.5 on this side, which is equal to 1.5 raised to y. Okay. What should be the exponent that when 1.5 raised to is equal to itself? The answer is 1, right? So when 1.5 raised to 1 is equal to itself, so that means in this case, we know that y would equal to 1. And again, if you don't know this, or if you don't understand this, what you need to do is you just need to take log again on both sides, right? So take log on both sides, so that way you bring y down. Okay, so in this case, it's going to be log of 1.5 equal to y log of 1.5, and then you are going to divide log of 1.5 on both sides. You are going to get y equal to 1. So now we know that this reaction is going to be second order with respect to nitrogen monoxide and first order with respect to oxygen. Okay, so the overall order for this would be 3, right? Or third order. This is third order reaction overall. Now, what is the rate constant with the proper unit for this, right? So again, because K is the constant, you can choose any trial. It's going to give you the same value. So in this case, I'm going to choose trial 2. Okay, so I'm going to choose trial 2. Okay, so if I choose try 2, I'm going to plug in try 2 with this rate expression. Okay, so it's going to be 1.29 times 10 to negative 2 molar per second equal to K. Multiply concentration of nitrogen monoxide 0.030 molar square. Multiply by concentration of oxygen 0.0038 molar. All right, next thing is just solve for this, right? So 1.29 times 10 to negative 2 molar per second equal to K. And then I'm going to do this operation right here. Okay, so don't forget there's square right there. Okay, so what we're gonna do is that we're gonna multiply 0.03 squared by 0.0083, and you are going to get this number right here. Now let's take a look at unit real quick. Okay, so you are going to if you're looking at unit, right? So this is this whole term right here is square. So that means when you square, you have to square unit as well. So you get molar square, but that molar square also multiplied by another molar. So in this case, the unit is going to come out to be cubic molar. Okay. The next thing is divide both sides by this whole thing. And what you're gonna do is that you are going to be able to get rid of one of these m as well, right? So this is 1m, this is 3m. So eventually on the bottom, you're gonna have m squared left. So that means your K would come out equal to 1.7 times 10 to the third, 1 over molar square times second. Okay, so or another way to do this is going to be the unit of m raised to negative 2 times second raised to negative 1. Okay. This big value of K, right, is a huge value, is 1,000 value here, is tell us that this reaction occur pretty fast in comparison to the first one that we see previously. Now we know the rate constant K, we know the order reaction with respect to each of the reactant. Therefore, we should be able to find out the rate of other condition as well, for example, in D right here. Okay, so in order to find out D, right, so all you need to do is that you need to find out the rate, right? So rate is going to equal to K, which is going to equal to 1.7 times 10 to the third, which what we calculated previously. Okay, and then multiply this by concentration of nitrogen monoxide, which is given as 0.125. Okay, so remember this is second order, so don't forget that second order as well. And then multiply by oxygen 0.125 molar, and this is raised to 1. So what you are going to do is that you are going to square both number and unit, right? So in this case, this molar square would eventually cancel out. Okay, so don't forget to square the number as well. If you do the math correctly, your rate would come out equal to 3.3 molar per second, right? Because you have molar here and you have per second there. Okay, so D would be 3.3 molar per second. Now, the next thing we're going to take a look at is we're going to take a look at the conceptual problem. Okay, so this problem giving us the rate law expression already. Okay, so it's this one right here. According to this rate law, we see that the rate is going to be directly proportional to x, right? Directly proportional to square of y. Okay, so in this case, we can say that it's first order with respect to x, and then second order with respect to y. Okay, and then it's the third order overall. All right, so in this case, what you will need to do is that you will need to looking at how changing of x and y would affect the rate. Now, if you're looking at this rate expression, right, we know that the rate is directly proportional to x, right, and also is directly proportional to y squared. So that means if you double x and also you double y, you are going to increase the rate by a factor of 8, right? So that means in this case, C would be the answer. Okay. Now let's take a look at B. Okay, so B, we are looking at the unit of the rate constant. So in this case, we're gonna look at the unit of K. Okay, so from the previous chapter, when we talk about the rate, right, we know that it's the change of the amount, right, per the change of time. So that means in this case, the unit of the rate will always going to be molar per second, right? You have amount per time here. Okay. For the concentration, is always going to be molar, right? So in this case, for X would be molar, Y would be molar, but remember Y is going to be second order, so that means you also need to square that unit as well. So if you do this, you are going to get molar over second, right, for the rate equal to K, and then you combine these two, is going to be what, cubic molar. Okay, so, and then you do some rearrangement. Okay, so divide both sides by molar cubic molar, you are going to get those two cancel out. You are going to get K equal to per molar square and per second. Okay, so or M to -2 and S to -1. Okay, so that's how you calculate for the rate constant. So that means in this case, the units of the rate constant is going to depend on the reaction order. Right? So it's going to affect by this power of each of those reactants. Okay, so that means in order to find out what is the unit of the rate constant, you will need to actually set up this type of calculation to find out the proper unit. In summary, in this video, we're looking at the differential rate law. We're looking at the rate expression, right? When we write out the rate equal to K and with different reactants, and we learn how to calculate for the reaction order with respect to each of those reactants as well. And you learn how to calculate for K value and proper units, right? And also you're looking at the graph and what does it mean when it's zero order, first order, and second order. Okay, so after finishing this video, I would like you to start working on homework 12.4 as soon as possible.